Welcome to The Explainer. Today we're diving into something that honestly seems completely ordinary at first glance. It's a white, powdery solid. You might walk right past a jar of it in a chemistry lab without even a second thought. But beneath that boring exterior lies a world full of strange paradoxes and absolutely fascinating chemical survival tactics. Today, we're unraveling the true nature of aluminum chloride.
So, what connects the high-octane gasoline fueling your car to the delicate, complex perfumes you might wear? Kind of sounds like a riddle, right? Well, the answer isn't some rare, exotic material locked away in a vault somewhere. It's actually the very chemical compound we're breaking down today. Before we even look at a single chemical formula, just keep this wildly contrasting range of applications in the back of your mind. We are dealing with a substance that literally bridges heavy industry and high-end cosmetics.
Okay, let's dive into Section 1, the preparation trap. Because getting your hands on the absolute purest form of this stuff is notoriously deceptive.
We're basically dealing with two very different beasts here: hydrated and anhydrated aluminum chloride. The hydrated version is your standard one. You make it simply by dissolving aluminum or its amphoteric oxides in dilute hydrochloric acid. It's a standard neutralization reaction, giving you salt and water. Once that solution crystallizes, water molecules are locked right into the actual structure of the crystals. But the anhydrous version, that requires absolute zero water, literally not a single drop. And trying to get from that first hydrated form to the second is exactly where the trap lies.
Logically, you'd probably think, well, hey, I have hydrated crystals, I want to remove the water, so I'll just heat them up. And for most chemical compounds, that works perfectly. You just bake the moisture out, and you're left with a dry, pure solid. But heating hydrated aluminum chloride crystals leads to a total breakdown. Instead of evaporating the water to leave a nice, pure compound, the whole molecular structure just falls apart. You end up with aluminum oxide, a cloud of hydrochloric acid, and water vapor. It's a complete chemical dead end.
So chemists had to get clever. To successfully capture that anhydrous version without destroying it, we have to use a very specific recipe. Step 1. Take a mixture of aluminum oxide, dry chlorine gas, and coke, and that's the pure carbon fuel, obviously, not the soda. Step 2. Heat that specific mixture up to a really high temperature. And Step 3. It yields our prize, anhydrous aluminum chloride, along with carbon monoxide gas as a byproduct.
Now there is an alternative method too. You can actually skip the oxide entirely and use direct combination. You just heat pure aluminum powder directly with completely dry chlorine gas in a specialized tube, and then carefully condense the resulting hot vapors in a receiver. Both of these methods brilliantly bypass that frustrating water trap entirely, giving us the pure, dry compound we need.
Moving right along to Section 2, Quirks and Properties. Now that we've successfully synthesized it, let's look at this compound's incredibly unique character profile.
Physically, pure aluminum chloride is a colorless, crystalline solid, but it behaves kind of strangely. When heated to 458 Kelvin, it sublimes, meaning it completely skips the melting phase and vaporizes straight from a solid to a gas. It's highly soluble in water, but it also readily dissolves in organic solvents like alcohol and benzene. It even has this tendency to form complex addition compounds with other substances, like ammonia, which really shows off its reactive, versatile personality.
Now, what's really interesting here is this specific trait. It is deliquescent. It's a fantastic word, right? Basically, it means if you leave this dry solid sitting out in the open, it eagerly absorbs atmospheric moisture. It literally pulls water right out of the air around it until it completely dissolves into a clear puddle. It's almost like the solid is actively drinking the humidity in the room until it drowns itself.
But wait, here's another major twist. Aluminum chloride is largely covalent. Normally, we think of compounds made from a metal and a nonmetal as purely ionic, full of charged particles zipping around, ready to carry an electrical current. But because of its covalent nature and a total absence of free-flowing ions, it stubbornly refuses to conduct electricity, even when it's fused or completely molten. It acts much more like a nonmetal compound in that regard.
So what happens when it finally hits a pool of water? Well, the resulting aqueous solution becomes highly acidic. This happens because the aluminum chloride undergoes a process called hydrolysis. This chemical reaction essentially splits the water molecules, creating a strong acid and a weak base. The strong acid completely dominates the weak base in the mixture, leaving the entire resulting solution highly acidic and pretty corrosive.
All right, Section 3, the dimer puzzle. This is really the structural climax of our explainer. We mentioned earlier that it sublimates into a vapor and dissolves in inert organic solvents, while how it structurally exists in those states is a brilliant story of chemical survival.
6. Now, in chemistry, this number represents a serious shortage. Aluminum naturally has 3 valence electrons in its outer shell. When it forms aluminum chloride, it shares 1 electron with 3 different chlorine atoms. 3 plus 3 equals 6. The central aluminum atom is stuck with only 6 valence electrons.
But, as we know, atoms desperately want 8 electrons. They absolutely need to complete their octet for total chemical stability. That's the golden rule of chemical bonding. Our aluminum here is deficient. It's short by 2 electrons, leaving it highly unstable, reactive, and frantically searching for a lifeline.
So, here is the brilliant team-up that actually solves the problem. The molecules form a dimer, which is essentially 2 identical molecules joining forces to form Al2Cl6. Instead of just relying on standard covalent bonds, this newly combined structure uses 2 special coordinate bonds alongside the 6 regular covalent bonds. A coordinate bond is unique because one atom donates both of the shared electrons rather than each atom chipping in one.
So the crucial point is, it all comes down to survival via sharing. Since the aluminum is 2 electrons short, it accepts a lone pair of electrons from a chlorine atom of a completely different aluminum chloride molecule, and the second aluminum atom does the exact same thing with the first molecule's chlorine. They share resources via these 2 coordinate bonds, perfectly completing the octet for both aluminum atoms without needing any outside help whatsoever. It's incredibly elegant.
Which brings us to Section 4, Real-World Applications. Let's shift our focus from all this complex structural chemistry to its everyday impact, because mastering this quirky compound has genuinely shaped massive parts of our industry.
And this brilliantly illustrates exactly why we should care about it. Aluminum chloride isn't just some dusty laboratory curiosity. It's a frequently used, absolutely crucial catalyst in the Friedel-Crafts reaction, which is a foundational process in organic chemistry. It's essential in manufacturing gasoline through the cracking of mineral oils, and it's a vital, often hidden ingredient in the production of paints, synthetic dyes, life-saving drugs, and yes, those delicate perfumes we mentioned at the very beginning of the explainer.
It's just a simple, incredibly quirky, covalent compound that's literally shaping the modern world. From that deliquescent, trap-filled preparation process to the clever little electron-sharing dimer trick, it transforms from a basic chemical equation into a foundational pillar of modern commercial industry.
I'm going to leave you with this final, lingering thought. If this single, weird compound is quietly shaping everything from the high-octane fuel in your car's tank to the expensive fragrance on your wrist, what other fascinating chemical secrets are hiding in the completely ordinary objects around you right now? Something to think about. Keep questioning, keep learning, and thank you so much for joining me for this explainer.